In this video, we talk about capacitors. We see what is a capacitor and how it works in the time and frequency domain. A basic capacitor is composed by two plates with surface A at a distance d, one from the other. Between the plates there is an insulator which can even be air. If we put charge in a plate, it attracts an opposite charge on the other plates. Because of the charge, an electric field is created between the plates. Ideally, the capacitor keeps the charge indefinitely, even when it is disconnected. Actually, charge can escape through the air or through the insulator, so after a while the capacitor discharges. So the capacitor works as a battery, because it stores charge. Intuitively, the larger the plate, the more charge it can store. The property of storing charge is called capacitance and is defined with C letter. In this case, a capacitor composed by two parallel plates with area A at a distance d has a capacitance equal epsilon times A divided by d, and it is measured in farad, where epsilon is the permittivity of the insulator, and the larger the better is the insulator and the higher is the capacitance. Because of electric field E, a voltage is created between the plates, and applying Ohm law we get an important equation, Q equal C times V. So, fixed the voltage, the larger is the capacitance, the larger is the charge and the energy we can store in the capacitor. Let's see now the real working of a capacitor. We imagine to charge a capacitor through a resistor because in every circuit there is a resistance, and even a capacitor shows some resistance. We analyze how vary the voltage across the capacitor as time function. At the beginning, the capacitor is discharged, so its electric field is zero, and its voltage is zero as well. So all the voltage V is applied to the resistor. For Ohm law, this implies the following of a current I equal V divided R in the circuit. So some charge is moving on the circuit to the capacitor. The charge starts to be stored in the capacitor. The storing charge creates an electric field which in turn creates a voltage across the capacitor, V1. Now the voltage across a resistor decreases because of the rising voltage across the capacitor, and the current decreases as well. This time is V minus V1 divided by R. So less charge is flowing and less charge is coming to the capacitor. So the charge and the voltage increases but less than before, and the current has a further decrease. The process goes on in this way. Always less charge is moved to the capacitor and the voltage tends to the final value of V following an exponential law. This exponential law comes applying Kirchhoff's law and solving the equation. When capacitor voltage is equal V, the current in the circuit is zero. So after a while, when the capacitor is fully charged, no current flows on the circuit. The capacitor is like an open circuit. There is no electrical continuity. There is an insulator indeed. So it is expected that current cannot flow through the capacitor. If we now disconnect the capacitor from the voltage supplier and create another path for the capacitor, we see the charge starts to flow again, discharging the capacitor. Here you have all you need to understand capacitor behavior. Capacitor prevents current from flowing, but only in stable condition, after a while. So capacitor is like an open circuit in direct current or DC condition. But you saw when we connect it to power supply or when we disconnect it, current can flow. So in variable condition, current can flow. The truth is current cannot flow through capacitor, so through the insulator, but for a while it can flow to the plates, charging and discharging the capacitor itself. Current can flow because you can add charge to the plates of the capacitor for a while. But how long is a while? Intuitively, The larger is the capacitance, the longer is the time we need to charge it, because the capacitor can store more charge. So at the end, with larger capacitance, we need more time to reach the same level of voltage, and with smaller capacitance, we need less time to reach the voltage. So smaller capacitors are faster in some way. They reach the voltage faster. Keep in mind this concept because it is important for the frequency behavior. Smaller capacitance is faster to reach the final voltage. Now let's imagine we have a variable supply voltage, a signal like this. This signal has a precise frequency. It always varies the same way. What happens to our capacitor? How does the voltage vary? Let's imagine to have a large capacitance, so as we said, very slow. When the signal rises, voltage in the capacitance increases, but slowly, like this. And when the signal goes down, it starts to decrease, but always slowly, and so on. The signal keeps to go up and down, and the capacitor voltage tries to follow the signal going up and down. But because the capacitance is large, or because the frequency in which the signal varies is too high, the voltage across the capacitor doesn't move too much. If we now increase the frequency of the signal, we see the voltage across the capacitor moving even less. If we keep increasing the frequency, we see the capacitor voltage barely moving. So at high frequency, capacitor doesn't feel anything. The voltage across its ends doesn't move. On the contrary, at low frequency, the voltage across its ends follows the signal, because you can move the charge enough fast to follow the signal. So capacitors behave differently at different frequencies. At lower frequency there is a voltage. At high frequency there is a much less voltage across the capacitor. In any case, for Ohm's law, when a current creates a voltage on a component, we have an impedance. So Ohm's law becomes V equal Xc times I. Xc is the capacitor impedance, and it measures the resistance to the flowing of the current at different frequencies. This is the impedance formula, and you see it is inversely proportional to the frequency. The larger the frequency, the lower the impedance, so the voltage across it. Here you can see also that another way to lower the impedance is increasing the capacitance. The larger the capacitance, the lower the impedance, and the lower the voltage across the capacitor. So this is the frequency characteristics of capacitors. You can see as the frequency increases, the impedance decreases, so less resistance to the flow of the current. So at very high frequency, capacitors behave like a shortcut, like wires. On the contrary, at very low frequency, capacitors show very high impedance, and they behave like open circuit. You can see at the same frequency, small capacitors show higher impedance, so more voltage drops on them, so they can follow better input signals. Beyond a certain frequency, the impedance starts to rise. This because in the real capacitor, permittivity becomes frequency dependent beyond certain frequency. A component with such characteristics is very useful. For example, imagine to have an integrated circuit which needs stable power supply and a supplier V which sometimes has some spikes and some disturbs. In order to prevent disturbs to affect the integrated circuit, we can put a decoupling capacitor between power supply and IC. The capacitor has to be enough large to block the disturb frequency. If the frequency is enough high for the capacitance chosen, the signal doesn't affect the voltage on the capacitor, which stays stable, cutting all the disturbs. Another use is the coupling capacitor. It blocks the direct signal and allows the high-frequency signal to pass. In this way, we can separate the DC setting of circuit 1 and 2 without the risk of mutual influence, but allowing the AC signal to pass. An important use of capacitors is in filters. This circuit, for example, cuts all the high frequencies. We saw it already and we understand that at high frequency the capacitor cannot follow the input signal, so it cuts it. At low frequency the capacitor follows the input signal, which passes through almost unchanged. So the frequency characteristics is this one. This is called low pass filter because only low frequencies can pass through. In this case, we see the high frequency passes through from V-in to V-out because at high frequency V-in drops wholly on the resistor R. As we said, at high frequency capacitor cannot follow the signal, so the voltage across it cannot change. At low frequency capacitor follows the V-in movement, so the voltage drops wholly on the capacitor, which charges and discharges, and no voltage pass through. So the low frequency is cut off. So the frequency characteristics is this one, and this circuit is called the high pass filter. Please leave me a comment and let me know if you liked this video. Make sure you put that thumb up, click the notification bell and subscribe to my channel.